All right, so for what values of R is the sequence R to the nth power convergent? Well, if we look at the limit and we break it into a couple of categories, if R is between -1 and 1, so like, let me give you an example. Give me a number between -1 and 1. So if R is 0.5, then you have um, the sequence 1/2 to the nth power, right? 0.5 is 1/2, which is 1 over 2 to the n. And then if we use our intuition, the limit as n goes to infinity of 1 over 2 to the n, the denominator is getting infinitely large, the numerator is staying constant at 1. That's going to approach 0, right? And that would be the same for any value between negative and positive 1. It would be the same idea that the numerator would get infinitely large, either positive or negative. It works with like -1/2 as well, right? So if I had -1/2 to the n, that's just -1 over 2 to the n. And if I let the limit go to infinity, then I still just have a constant over something that's growing infinitely large, which is still going to approach 0. So if R is between negative and positive 1, the limit will be 0. If R equals 1, the limit will be 1 because 1 to any power is still 1. And so we're going to define some language regarding sequences. We call a sequence increasing if a sub n is strictly less than a sub n plus 1 for all n greater than or equal to 1. And decreasing if the opposite is true. So if we flip that inequality, a sub n is greater than a sub n plus 1 for all n greater than or equal to 1. And then the language, we call it monotonic if it's either increasing or decreasing. Okay. So let's talk about the sequence 3 over n plus 5. And how would we prove that it's decreasing? Well, if a sub n equals 3 over n plus 5, then a sub n plus 1 would be 3 over n plus 1 plus 5, which is just 3 over n plus 6. And then if I compare those two, oh, thanks. How does 3 over n plus 5 compare to 3 over n plus 6? Which way should my inequality be going? Remember, n is a positive constant, yeah. Yeah, I will. Let me just finish this inequality. Which way should the inequality go? How does 3 over n plus 5? Yeah, the smaller denominator will be the greater value. So now that then we've shown that a sub n is greater than a sub n plus 1 for all n greater than or equal to 1. Therefore, our sequence 3 over n plus 5 by the definition is decreasing, right? So that's how you prove a sequence is either increasing or decreasing. You look at a sub n, and then you look at a sub n plus 1, and then you decide which way the inequality would go. And then you make a statement, it's either increasing or decreasing by the definition of increasing and decreasing. There you go, Claire.
To a non-monotonic, is there a different word for non-monotonic?
Nope, you got it right. So that would just be like a sequence that's either oscillating or it's not always increasing, like it could do this and then increase from there, but it's not strictly increasing. All right, let's try another one. So show that the sequence a sub n equals n over n squared plus 1 is decreasing. So this one isn't as simple or trivial as the last one was, but we're going to take the same approach. So a sub n is equal to this. So then we want to compare that to a sub n plus 1. So a sub n plus 1. Just replace all the n's with n plus 1s. We're going to have n plus 1 over n plus 1 quantity squared plus 1. So we want to show that it's decreasing, meaning we want a sub n plus 1 to be less than a sub n. So I need n plus 1 over n plus 1 quantity squared plus 1 to be less than n over n squared plus 1. Now, that's not immediately obvious just looking at that it's true. And to be able to prove that this inequality is true, it should be obvious just upon inspection. All right, so what we'll do, let's go ahead and cross multiply, which is fine and won't affect the inequality because remember, n is only a positive whole number, right? So we don't have to worry about like, if n was negative, then when we multiply by both sides, we would have to flip the inequality. We don't have to worry about that here. N is just positive, so we can cross multiply, and I get n plus 1 times n squared plus 1 is less than n times n plus 1 quantity squared plus 1. All right, and then we're just going to expand these. So I'm just going to FOIL these out. So I get n cubed plus n plus n squared plus 1 is less than all right, hold on. That's going to be n times n squared plus 2n is going to end up being plus 2. All right, n cubed plus n squared plus n plus 1 is less than n cubed plus 2n squared plus 2n. And then we can start canceling like terms on either side. N cubed gone. I'll go ahead and subtract the n squared and the n from both sides. And I get that 1 is less than n squared plus n. And that's immediately true because remember, n starts at 1. So n is strictly greater than or equal to 1. If we plug in 1 there, we get 1 is less than 2, which is true. Right? Therefore, our sequence an is decreasing. Okay. Couple definitions. A sequence is bounded above if there is a number m such that a sub n is less than or equal to m for all n. And it's bounded below if there's a number lowercase m such that m is less than or equal to a sub n for all n. If it's bounded both above and below, we call it a bounded sequence. Bounded, let's say above, and it's strictly increasing, that's going to mean it continues to increase forever, but it doesn't go above its boundary. So it's going to converge to that boundary. It has to, right? If it's decreasing and it's bounded below, same idea. It doesn't ever go below that boundary, lowercase m, so this would be uppercase m, this will be lowercase m. So it must converge to that lowercase m. All right, here's a fun one. This is a new way to prove things. So we've talked about a couple kinds of proof. We've seen direct proofs. And then in this class, we've seen proof by contradiction at some point. And there's a new one that's called the principle of mathematical induction. And I think of this kind of as the domino effect. This works really well when you're trying to prove something about the positive integers. And since sequences deal with the positive integers a lot, because they're indexed by that, right? A1, A2, A3, A4, and so on. This works well for proofs about positive integers, but I remember learning this like when I was a freshman in college, and it was so hard for me to wrap my head around. So please let me know if you have questions. All right, so we're trying to prove a statement Sn about the positive integers, or about the positive integer n. Here's what you do. You assume S1 is true. No, I'm sorry, you don't assume. You show that S1 is true. Then you show that Sk plus 1 is true whenever Sk is true. And if you can show that, since you've already shown S1 is true, then S2 must be true. And if S2 is true, then S3 must be true. And if S3 is true, then S4 must be true, and so on, out to infinity. So that sounds really abstract. We will do an example, and hopefully it'll help it make more sense. Okay. So to do this, we're going to investigate this sequence that's defined recursively. So they tell us that A1 is 2, A1 is defined by 2, and then they tell us that AN plus 1 is equal to half AN plus 6. All right, so we're going to need a calculator. So we're going to look at the first few terms and come up with a conjecture about what we think is going on. And then we'll kind of try and prove our conjecture. And that's where we're going to use that mathematical induction principle. All right, so we know A1 is 2. So then A2, using the recursive definition, would be 1/2 times A1 plus 6. Well, A1 is just 2 plus 6. So that's 1/2 times 8. So A2 is 4, not 8. Oh Oh my God. All right, so what does A3 look like? So it's always the next one in line is half the previous one plus 6, right? So A3 is going to be half what? Good. Half 4 plus 6. So A3 is 5, right? Let's do a couple of these until we can decide whether we think this sequence converges or diverges. And if we think it converges, I want a conjecture of what it converges to. So A4 is half what? So that's half of 11, 5.5. So A5 is half 5.5 plus 6. All right, so now we're getting into calculator territory. So what's half of 11.5? It's 5.75, right? A6 is half 5.75 plus 6. So that's 5.875. A7, half 5.875 plus 6. $5.9375. Any guesses? Do you think this converges or diverges? What do you, if you had to guess, what would you think it converges to? Okay. So conjecture. The limit as n goes to infinity of a sub n is 6, is what you're saying, yeah? Okay. So how are we going to prove this? So first, let's prove that it converges. And you think 6 is the upper boundary, yeah? So we can use the monotonic sequence theorem. So if we can prove that this is increasing and it's bounded up top by 6, then we can say that it must converge by the monotonic sequence theorem, right? By that last, this guy here. If it's increasing and we prove that its upper boundary is 6, then it must converge, right? All right, so first, let's see if we can show that it is increasing. All right, so I'm going to go prove increasing. And we're going to use induction to prove this. So S1, we want to show that it's, S1 is show that it's true for some term. So we can show that it's true for the first two terms. So that would just be that A2 is greater than A1, right? So A2 is greater than A1 because A2 is 4 and A1 is 2 and 4 is greater than 2. So we've completed the first part of mathematical induction, which is just show that it's true for the first part. Okay?
Mr. Toller, can you truly prove to me that 4 is greater than 2?
All right. So now we want to show that it must be true that sk plus 1 is true when sk is true. So for that, we want to show that a sub k plus 1 is greater than a sub k. And here's how we're going to do that. We're going to recreate our sequence. So what I'm going to do is add 6 to both sides. So ak plus 1 plus 6 would then be greater than ak plus 6. And then I'm going to divide by 2, or multiply by 1/2 rather, 1/2, 1/2, so that inequality would still hold. So all I did was add 6 to both sides and multiply by 1/2. We'll notice that this is the formula for what term? Look back up here. Maybe it's easier if we start on the left, or on the right rather. 1/2 times the quantity ak plus 6. Wouldn't that just be the definition of ak plus 1? So I can replace the right-hand side with ak plus 1. But then the left-hand side would be the definition of what term in my sequence. If I multiply 1/2 ak plus 1 plus 6. So if this equals ak plus 1, this is just the next term in line, right? Which would be ak plus 2. So here's what I've shown. I've shown that if ak plus 1 is greater than ak, then it must be true that ak plus 2 is greater than ak plus 1. So think about this. That means that if, let's put it in concrete terms as a concrete example. If a2 is greater than a1, then I've shown that that means that a3 must be greater than a2, right? Right. Which means that if a3 is greater than a2, and I go back up here, okay, so now I know a3 is greater than a2, then that means a4 is greater than a3, right? And if a4 is greater than a3, then that means that a5 is greater than a4. And if a5 is greater than a4, then a6 is greater than a5, right? That,
So you're proving that this can just go on forever.
this goes on forever. So since I already showed empirically up here in my first statement that a2 is greater than a1, okay, so now I know a2 is greater than a1, and then I proved that, okay, well, if ak plus 1 is greater than ak, then ak plus 2 is greater than ak plus 1, whoops, then a1. So now I've shown a3 must be greater than a2. And then we can go back up here and start it over. Okay, so then a3 is greater than a2, then that means a4 is greater than a3. And that goes on forever. And we've proven that the sequence is increasing. Yeah.
So I get like the first part, but what is S1? I'm not understanding what that is.
It's just a statement, it's a concrete statement that shows it's your starting point. So S1 is making the statement. From my sequence, I've shown that the second term is bigger than the first term.
So if you were trying to prove that it's decreasing, the S1 would be like A1 is less
yeah, you would be showing that the second term is less than the first term. And then SK is, then we abstract it, right? We go, okay, if this first term is true, then the next thing must be true. And then since you have from S1 a concrete starting point, once you've proven that, you can go out to infinity. It's like the domino effect. Go ahead. Yes, absolutely. So that comes from, so Claire asked me to explain how I got from basically this to this, right? So that comes from this definition up here. And so maybe if I do it in terms of n. So a sub n plus 1 is 1/2 a sub n plus 6, right? So the next term in line is half the previous term plus 6, right? So that means if I went to the next term, which would be a sub n plus 2, I would do 1/2 the previous term, which is a sub n plus 1 plus 6, right? So that's where the a sub k plus 2 comes from. All right, so I can say then, therefore, an is increasing. Hey, so we'll do a little more practice with induction here. So we know it's increasing, but now I want to prove that it's bounded, and specifically we think it's bounded by 6, right? All right, so we're going to use induction for this, and I've run out of room. So is everybody good with what's down right now? Because I'm going to erase some stuff. All right, so prove bounded. Prove bounded above by 6. All right, we're going to use induction again. So my S1 statement here, I'm trying to prove that it's bounded above by 6. My S1 statement is I'm just going to take my first term and make the statement it's definitely less than 6. So A1 is less than 6, right? Because 2 is less than 6. Don't ask me to prove that, Alex. We're going to assume that's true. All right, and then we want to show S sub k plus 1 is true when S sub k is true. Okay, and we're kind of going to do the same thing. So we'll assume S sub k is less than 6. Then I'm sorry, I meant not S sub k, I meant A sub k. That's a term in my sequence. A sub k is less than 6. Then if I add 6 to both sides, that inequality should still stand. So a sub k plus 6 is less than 6 plus 6. And then if I multiply by 1/2, a sub k plus 6 is less than 1/2 of 6 plus 6. But what do I have on the left-hand side? What is that the definition of? 1/2 a sub k plus 6. That's the definition of a sub k plus 1, right? So then a sub k plus 1 is less than 6. Boom. So I just showed that if a sub k is less than 6, then it must be true that a sub k plus 1 is less than 6. And I have a starting point. I already showed that a sub 1 is less than 6. So this proves then that a sub 2 is less than 6, right? And if a2 is less than 6, then this proves that A3 is less than 6. And we could go towards infinity. So all terms have to be less than 6, right? All right, therefore, A sub n is less than 6. All right, so we've proven that it is increasing, aka monotonic. We've proven that it's bounded above by 6. It's clearly bounded below by 0, right? Because the first term is 2 and it's increasing. So it's both monotonic and bounded, meaning it must converge. So I'm going to make that statement. So therefore, A sub n converges by the monotonic sequence theorem. But we haven't necessarily proven that it has to converge to 6. All right, so how are we going to prove that it converges to 6 exactly? So prove that, that's not a good T, converges to 6. All right, so we already know it converges. Let's assume that it converges to something. Assume the limit as n approaches infinity of A sub n equals capital L, right? Well, if we take the limit as n approaches infinity of A sub n plus 1, isn't that going to be the limit as n approaches infinity of 1/2 A sub n plus 6? Just by the definition of what A sub n plus 1 is. And what did we just say that this A sub n is going to go to as n approaches infinity? Now we're trying to prove it goes to 6, but what do we say in the line above that it goes to? We know it converges, but we don't know that it goes to 6 yet. L. So this just is going to become L, right? So this equals 1/2 capital L plus 6. Now A sub n and A sub n plus 1 are the same sequence, correct? A sub n plus 1 is just one term ahead in the sequence, right? But if they converge, they have to converge to the same thing because they're the same sequence. Meaning L has to equal 1/2 L plus 6, right? And L is what they converge to. Now we just have an algebra problem. So this is L equals 1/2 L plus 3. Subtract 1/2 L over. 1/2 L equals 3, multiply by 2. L equals 6. Therefore, A sub n converges to 6. Awesome. Whoops, sorry, I'm off the screen. There you go. That's a good one, man. That's some real proof in theory mathematics.
Will this be on a quiz or test?
I think there is.
That was pretty rough.
I think there is proof by induction, but it's not this crazy. All right, and that's it for the problem. problem set you guys have on 11.1 problem set. We didn't get to 11.2. We'll probably start it tomorrow, but I doubt we'll get all the way through it. It's an introduction to series. Turn off. Yo.
Can you post the 11.1 problem set answers?
Yeah, I will. All right, so you got an 11.1 problem set to work on. I'll give you the rest of the period to work on that. When you're done, just scan and upload it. Zoomers, feel free to log off. Yeah, I'll go ahead and post the answers in the supplemental section.